Now that we have the basic rules for writing electron configurations and orbital diagrams, at least presented to us, hopefully at least partially understood, let's look at a few examples here and then actually work some out ourselves. So the examples shown here and on the next slide are elements 3 through 10, starting here with lithium and going up through neon. And if you remember back from very, very early on in the class, the number of electrons is just going to be the same as the atomic number. We will take a look at some ions later, but for now we're just looking at the plain old elements here. We're not worrying about ions yet. And so with something like beryllium, which has 4 electrons, we're going to start with the 1s, which is the lowest energy orbital or subshell, and we're going to put 2 electrons in there, and then the next 2 are going to go into the 2s, and it can hold 2 electrons, and so that is the complete electron configuration since it only has 4 electrons to give. And the orbital diagram would then just be those 2 subshells, each having just a single orbital and 2 electrons each. In more complicated ones, here like in nitrogen, it has 7 electrons, and so we would put the first 2 in the 2s, in the 1s, the next 2 in the 2s, and then we'd have 3 left, and so those would go into the 2p, and again, because of Hund's rule, we would put them into their own orbitals with parallel spins, either up or down. It's just usually it's written as up. Alright, so you can take a look at those other examples there if you would like to, but for now I think I'm going to go ahead and start to work some of these practice problems. So if you feel like you have a decent grip on how to write these electron configurations, go ahead and pause the video here and write out the electron configuration for each of these things, for krypton and rubidium. You do not have to write the orbital diagram for these, just the electron configuration, which would be this version here, just the 1s2, 2s2, 2p6, and so on. So go ahead and pause the video and work that out. Alright, so the very first thing that you want to do when you're writing out an electron configuration is figure out how many electrons do I have? Do I have 5? Do I have 10? Do I have 55? Who knows? We need to figure that out. So if we look at krypton on the periodic table, it has 36 electrons. It is element number 36. We're not told that it is ionized or anything, and so it is going to have the same number of electrons as protons. And so what we're going to do is we are just going to start at 1s and fill in electrons until we run out. So we have 36 electrons to give. 1s is the lowest. It can hold 2 electrons because it has 1 orbital. 2s comes next. It can also hold 2 electrons. 2p is after that. It has 3 orbitals, which means it can hold 6 electrons. What's after 2p? 3s, it can hold 2. After 3s is 3p, which can hold 6. What's after 3p? If you said 3d, remember, this is where things start to get out of order. 4s comes after 3p. After that comes 3d. How many electrons can 3d hold? D sublevels, or subshells, have 5 orbitals in them, which means they can hold 10 electrons, 2 per orbital. So when I'm writing out an electron configuration and I don't know where it's going to end, I know pretty much where this one's going to end, but I'm going to go ahead and pretend like I don't. I always try to keep track of how many electrons I've put in. So thankfully, at the beginning here, the electrons pretty much separate themselves into groups of 10. So we have 10, 20, 30 electrons already into the configuration. So I have 6 more to give. If I check that handy-dandy guide here, I did 3p and 4s, 3d. After 3d, there is 4p. So if I come back here, 4p has 3 orbitals, 2 electrons each, means it can hold 6 electrons, and I have 6 electrons to give. And so that is the completed electron configuration. And by the way, that's supposed to be a lowercase p. It looks like an uppercase p. All the letters are supposed to be lowercase. All right, what about rubidium? Rubidium, if you look at the periodic table, actually has 1 more electron than krypton does. It has a 37. So we're just going to do the same thing. Start with 1s, which can hold 2. 2s can hold 2. 2p can hold 6 electrons. 3s can hold 2. 3p can hold 6. Again, this is where it gets a little mixed up. 3d does not come after 3p. 4s comes after 3p. 3d is after that, which can hold 10. I'm up to 30 now. 4p is after that. 4p can hold 6 electrons. And I still had 7 to give. So after 4p, I still have 1 more. And if you check our handy-dandy cheat sheet here, after 4p, we have 5s. 5s can hold 2 electrons, but I only have 1 more to give. And so it is 5s1 is how you would finish that configuration. So that is the electron configuration for rubidium, which has 37 electrons in it. Now you might be thinking, practically that entire configuration was exactly the same as the first one. We had the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. It's all the same for one and the other. This is always going to be the case. The electron configurations, how those sublevels split up, they do not change from one element to the next. The order of those is not different for krypton than it is for uranium. They are all the same. And so because of this, we kind of have a shorthand way of representing electron configurations. So we don't have to write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 every single time we want to write an electron configuration. Our shorthand way of writing these electron configurations is using what we call noble gas cores. Essentially what we're doing is we're taking a shortcut to say everything in the electron configuration is the same as this noble gas and its electron configuration, and then we pick up at that point and write the rest of the electron configuration. So for rubidium, for example, its entire configuration is the same as krypton up to this point. So its noble gas core configuration is krypton, and then everything that's different than krypton from that point forward, because krypton only goes to the 4p6. And so it would be krypton 5s1. Saying everything, all the core electrons are the same as krypton, and then after krypton we have this one extra. And so this is actually going to be pretty handy because it'll save us a lot of time when writing some of these configurations. The easiest way, by the way, to figure out where to start after a noble gas core is using the period numbers on the side here. So if, for example, we are starting with argon, So I wish they had these written in here, but this is helium, argon, krypton, xenon. My mind is going blank here. Yeah, krypton, xenon, radon is the next one. Yeah, radon. I always get radon and radium mixed up. Radium is down here, I believe. I think that's radium. Anyway, not important. So we have our noble gases here. So if, for example, you knew that you had some element in here, and so you wanted, whatever element this is, and so you wanted to use the noble gas core, you would just say, okay, what was the last noble gas before this element? That would be argon. And if you're thinking, well, but I don't know what comes after argon, I'm going to have to write out the whole electron configuration anyway. No, you don't. You don't have to work out the whole thing. The easiest way to figure out where you pick up with after the noble gas is to see what's the next element after that noble gas. Or more specifically, what row is that next element on. So after argon, the next element is on row 4. So you are going to start with the 4s. So after argon, it would be argon, and this particular element, whatever it is, we can work out the configuration for this one just using the periodic table and noble gas cores. So it has argon as its core. Pick up with the 4s's after that. It will have both of those because this is how the periodic table is split up. If you notice here, this block is the s block. It's 2 elements wide because you can fit 2 electrons into the s subshell. The d block is 10 elements wide because you can fit 10 electrons into a d subshell. The p block here is 6 elements wide because we can fit 6 electrons into a p sublevel. And then the f subblock we don't really care about, but it's the same thing here. We're not going to, well, I shouldn't say we're never. We'll rarely do stuff into the f subshell, but we might once or twice. But it is 14 elements wide because there are 7 orbitals, which means it can hold 14 electrons. But for our example here with this element, it has an argon core. Go down to the next element here, pick up with 4s, go all the way through the d's. So that would be 3d. The d's are always one behind whatever the period number is. So these are the 3d, this is the 4d, 5d, 6d. So we have all 10 of the 3ds. And then this next element here, that is going to be the 4p1. And that is the electron configuration for gallium. That's what that is. It's gallium. So using noble gas cores and using the periodic table as well can be very handy as a quick, easy way of working out what the electron configuration is for an element. And by the way, if you do need to use the F block when working out the using the periodic table, the F's are another one behind. So this is the 4F, and this is the 5F. So the D's start with a 3, and the F's start with 4. All right. So with that in mind, let's use the periodic table, and we'll go ahead and use noble gas cores as well to find the electron configuration for selenium. And selenium is 2 elements down from oxygen, which is right there. So this is oxygen, this is selenium. So to find the electron configuration for selenium, we are going to figure out what was the last noble gas before selenium. It's really close to krypton, but we can't use krypton. It's the one before. What was the last noble gas, not the next noble gas? So the last noble gas was argon. So we know that it's going to start with argon in square brackets. And then picking up from argon, we start with the 4s. So it's going to be 4s2. We're going to go all the way through the 3ds, so it'll be 3d10. And then selenium is 1, 2, 3, 4 elements in to the 4p. So 4s2, 3d10, 4p4. And again, this comes from, and if you want to double check to make sure that that is correct, you can always go back to our handy dandy guide here. It is 4s, 3d, 4p. That is indeed the correct order. So we fill up the 4s, fill up the 3d, and then we're 1, 2, 3, 4 electrons into the 4p. And that is selenium. Personally, I think this is the easiest way to work out an electron configuration, is using the periodic table and using where an element is located on the periodic table. If you're not comfortable with it, I'm never going to have a question where I say, only use the periodic table. Don't just work it out from the beginning. Like it's, if you want to work it out from the beginning and have 1s2, 2s2, 2p6, 3s2, do the whole shebang, you can do that. But I think it's easier to use the periodic table. All right, let's do a few more examples here. Magnesium has, if I remember correctly, 12 electrons. Let me double check that. Yep. Let's go ahead and write out the whole thing for magnesium because it's pretty small. So the electron configuration, and actually, why don't you do that on your own? Because you've gotten some practice now, so especially if you did not stop and practice the ones earlier, go ahead and pause the video here and try to work out all of these. And maybe do the last two using noble gas cores, just for practice. But you should be able to do it either way. But especially bromine. Bromine is not huge by any means, but it's 35 electrons. For sure, try bromine with the noble gas cores, and maybe aluminum as well. So go ahead and pause the video and try to work those out. All right. Aluminum is 13. So magnesium, we're going to go ahead and write out the whole configuration for magnesium since it's fairly small. You could do a noble gas core for it, but it's kind of a little bit of overkill. So we're going to have 1s2, 2s2, 2p6. That gets us 10 electrons. We only have 2 left, and so those go into the 3s. So that is the configuration for magnesium. For phosphorus, we only have 3 more, so it's going to be fairly similar to this one. So it'll be 1s2, 2s2, 2p6, 3s2, so that gets us to 12. We have 3 more to put in. After the 3s, we have 3p. It can hold 6 electrons, but we don't have 6 to give. We only have 3. So it's going to be 3p3. So that is phosphorus. We'll go ahead and do the noble gas core for bromine. Bromine is the 3rd halogen down. So if we go back here, this is bromine. So argon was the last noble gas before bromine. So we're going to pick up with the 4s after that. So we have argon, 4s2. We're going to go all the way across the 3ds, 3d10, and then if we count the number of elements into the 4p, 1, 2, 3, 4, 5 elements in to the 4p, which means that it is going to be 5 electrons in the 4p. So 4p5. Right, so the last one here, again, it's a little bit of overkill to do noble gas core on this, but it's good practice to do it anyway. So not argon, aluminum would have a noble gas core of neon. Neon is the last noble gas before argon. So why do I keep saying argon? Aluminum. This is aluminum right here. There. So neon was the last one. After neon, you pick up at the 3s, because it's on the third period. So we'd have 3s2. We skip over here, because there's no d's in the middle there. We go straight to the 3p, and it is the very first element on the 3p block, and so it's going to be 3p1. Alright. I think we'll do the orbital diagrams in the next video. But hopefully you're starting to get comfortable with writing orbital diagram, or not orbital diagrams, but electron configurations. I know when it's first introduced, it's just so foreign to what we've done up to this point, it can be kind of daunting, but it really is very straightforward. If you just learn the rules, you learn the order of the orbitals, it doesn't change from one thing to another. It is pretty straightforward, and if you work at it, it can be really easy points on an exam. So do your best to learn this stuff. And we will pick up in the next video.